Alright, my friends, this is a video on the photoelectric effect. Now, what I'm going to do is I'm going to give you some information on the photoelectric effect. I'm going to explain to you the photoelectric effect based upon a story that someone told me a long time ago, probably long before you guys were born. But this is the story that they told me, and I'm going to repeat that story. And from it, you should learn stuff about the photoelectric effect. So as you can see, this says mystery number 2, the photoelectric effect. This refers to the fact that the way atoms emit or absorb electromagnetic radiation was mystery number 1. And so this is mystery number 2, the photoelectric effect, and it was solved by Einstein in 1905, for which he won a Nobel Prize. Anyway, my friends, let's go over to the picture on the right. Oh, there's that bell. Let's go over to the picture on the right. What we have there is a metal plate, and we're going to pretend that metal plate is made out of sodium. It might be made out of some other type of metal, but we're going to use sodium because it's important to the example that we're about to discuss. So we've got this metal plate made out of sodium, and we've got this other metal pole there made out of a different material, and the two metal plates and the pole, the metal plate and the pole, are hooked up to a high voltage source, and there's a meter on there to show that there is a voltage source going on there, but it's also there to show that the flow of electrons. So if it's an ammeter, it's showing the flow of electrons, and it would make sense it's in an ammeter because it seems to be in the circuit, not across the circuit. So anyway, as you can see in this picture, light incident upon the metal plate causes electrons to move from the metal plate, which is negatively charged, to the positive post, which is positively charged. And so electrons flow from the voltage source through the meter, across the plates, back to the voltage source. So we have a complete circuit. And the reason we have a complete circuit is this because the electrons move from one metal plate to the other metal plate as they're placed under a voltage source, and it's due to light hitting them and causing them to be knocked out. Okay, so that means that the light has to provide enough energy to do two things. One, it has to provide enough energy, or what we call the binding energy. We're going to call it BE. So it has to provide enough energy for the electron to be pulled or removed from its position in the atom. The other energy that it also has to provide is a sufficient amount of kinetic energy in order to get the electron to move from point A to point B. So otherwise, if the electron doesn't have enough energy, it won't move from the atom in the metal plate to the post. Now remember, we said that we're going to pretend that that piece of metal is a piece of sodium. Well, it turns out that if you hit sodium with blue light, or indigo light, or violet light, or ultraviolet light, when you hit sodium with blue light, electrons will move from the sodium metal to the post, or the other metal post, which is positively charged. Henceforth, what you have is the photoelectric effect. You have light hitting a metal piece, causing electrons to be ejected and move from point A to point B. So blue light, or indigo light, or violet light will do that. Check. But when you go to use red light, or orange light, or green light, nothing. No electrons are released. Okay? So, they figured, based upon a classical model of physics, they figured, hey, let's do this. Let's make the red light brighter. If we make the red light brighter, the brightness, the intensity of the light should increase the amount of energy that the light has, and so it should now, at a brighter level, at a higher intensity, or a brighter light, should have enough binding energy and enough kinetic energy, or it should be able to provide, is what I'm trying to say, enough energy to remove the electron, so to give it the binding energy, and enough energy to get the electron to move from point A to point B. That would be its kinetic energy. Well, they turn up the brightness of the red light, and guess what? Nothing happens. It does not release electrons. Even though the light is brighter, right? Even though it's more intense, Even more, even though classically, physical wise, due to classical physics, we would expect it to have more energy. It still does not provide enough energy to remove the electron, the binding energy, and the energy for kinetic energy, even though we made it brighter. Classical physics can't explain this. That's a problem. I'm going to show you another conundrum, or at least talk to you about another conundrum. Another conundrum is this. Let's continue to hit this with blue light, because we know blue light will produce electrons. Check, right? Blue light has the energy necessary to produce, or has the energy necessary to remove the electron, therefore providing the binding energy, and enough energy to have the electron move from point A to point B. That's the kinetic energy. Now, let's hit this with blue light, and electrons are coming out, right? And they're thinking, what if we made the blue light brighter, more intense? What if we increased the intensity of the blue light? What's going to happen? Well, they figured classical physics should say that if we increase the intensity of the light, we're going to get those electrons to have more kinetic energy. Because remember, the blue light provides enough energy to remove the electron, the binding energy, plus the kinetic energy to make the electrons go from point A to point B. So the binding energy is pretty much constant. But if we increase the intensity of the light, now the blue light with greater intensity is going to have more energy, and it's going to pull the electron out like it normally would because the binding energy stays constant for the sodium atom. But now that extra energy is going to go into kinetic energy, and those electrons should have more kinetic energy. So we should see an increase in the amount of kinetic energy that the electrons have. And when they do this, the answer is no. They do not have more kinetic energy. But what they do notice is this, that more electrons are actually removed. They get more current. The current increases, right? So we get more amps, greater number of amps. Classical physics could not explain this problem either. So, how did Einstein fix this problem? Well, he said, basically, this, that light requires two models in order to explain its behavior. We already found out earlier that there is a wave model, okay? The wave model, the fact that light exists as both an electric wave and a magnetic wave propagating through space, and as they move through space, they change, and as they change, they intensify each other or keep each other moving along, and that's why you don't need a medium for light to travel through, okay? Because the electric portion of the wave and the magnetic portion of the wave, as they change, right, as the field changes, it causes the other one to be produced. So as each field changes, it produces the other one, therefore it propagates through space because it reinforces itself. But also at the same time, he thought that you needed a particle model, that the energy of the light, the energy of light is the particleness of it. The energy of light is quantized, just like Planck said about the energy emitted or absorbed by atoms. The energy is quantized, and that its energy is equal to h nu. So the energy of light is equal to h nu. Since the energy of light is quantized, it's a discrete little portion, a little bundle, a little packet of energy. He said he likened that to a particle, and he called it a photon. So a photon is a packet of energy, a packet of light energy that propagates through space, but it also acts as a wave. So it's got that wave thing going on, but it's got the particle thing going on. It's a little packet or bundle of energy. And the energy of a photon of light is equal to h times nu. So, that must mean, my friends, that h times nu has to equal to the binding energy plus the kinetic energy of the electron as it's removed from the sodium metal plate. You see, when the blue light hits it, okay, the energy of the blue light is not directly related to its intensity. It's directly related to its frequency. And so the energy of the blue light has to be sufficient to remove the electron, providing the binding energy, and the energy required to get the electron to move from point A to point B, the kinetic energy. So the energy of the light is now dependent upon its frequency. Well, apparently now, blue light has a high enough frequency to provide both of these energies in the correct amounts. Red light, unfortunately, does not. So if you increase the intensity of red light, remember, intensity is no longer what the energy of light is related to. It's related to the frequency of that light. Therefore, even if you increase the intensity, you still won't get electrons to come out, because it's not the intensity that determines the energy, it's the frequency. Red light just doesn't have a high enough frequency in order to remove the electrons and have them move from point A to point B. And so red light doesn't have it, but blue light does. We can also explain why we get more electrons when we increase the intensity of the blue light. Well, if we increase the intensity of the blue light, remember we said that doesn't affect the energy. What affects the energy is the frequency. So by making it brighter, you don't change the frequency. What you're doing is this. You're just increasing the number of photons. By increasing the intensity of the light, what happens is that the number of photons of blue light is increasing. And so as the number of photons of blue light increase, you're going to get more electrons. More photons, more little bundles, more little packets, more little discrete bundle or packets of energy hitting more electrons. More packets of energy hit more electrons are ejected from the metal plate. And this is how he explained the photoelectric effect and the issues or anomalies that could not be explained. Okay, if you have any questions, see myself or Mr. Walsh, and have a good day.